Thank you very much for the invitation and the opportunity to present my talk in collaboration with Amir, who is here. It is not a secret that it's hard to compute entanglement entropy, and in gravitational systems, it's especially hard because once you consider the replica copies, you can have wormholes jump between the different copies. Fortunately, you cannot really see this, but they're supposed to be like a plane. There are supposed to be two planes in this picture. And this wormhole connects the two replica copies. So in the recent years, there was lots of progress in understanding such contributions. But still, it would be nice to bound entanglement entropy from some simpler observables, which don't require replicas. And there is a universal way to do that, which is well known in the literature. So this slide looks a bit heavy, but I promise it's really elementary, so bear with me for a minute. So I have some spatial region R, and I have charge QR, which is just the integral of a local current over this spatial region. And also I have a reduced density matrix on this subregion. And what I want to claim first, that under very mild assumptions, these commute. And these assumptions are presented here. So I assume that I have just the total of my system, and the total charge commutes with the total density matrix. So this would happen, for example, if the total state is a thermal state or has a definite charge. And then I require the split property that the total charge is the sum of the charge inside R and outside R. So I leave it as an exercise for the bus ride to prove this. And then the density matrix can be split into different charge sectors, where in row Q I have all the states there have a fixed charge Q. And then I have these blocks, and I want to normalize each of them to 1. The trace of each trace of each one of them is 1, and then I just need to separate them multiplicative normalization, which is P of this function P of Q. So this P of Q, it's positive, and sum over all Q's is 1. Then even simpler exercise to write down von Neumann entropy using this decomposition. This is the same equation. So I have two terms. First, I need to compute the von Neumann entropy of each block, and then weight it with the corresponding distribution P of Q. And this is manifestly positive. But on top of that, I also need to add the Shannon entropy of this classical charge distribution. So this is what I will call fluctuation entropy. And since the first sum is manifestly positive, then I can bound the entanglement entropy from below in this fluctuation entropy. And it's really easy to compute. So if you P of Q is essentially the probability of the charge distribution in the subregion. So if I compute the expectation value of this operator, e to the I alpha QR, where alpha is some real number, then essentially it gives me the Fourier transform of the probability distribution, and I can easily invert it. So as you see, this observable here, it does not include any replicas. It's just a matrix element, but still one can derive very useful relations using this inequality. So to anticipate some questions, in QFT, all these free quantities are divergent, but in fact, we will be after the volume dependence in each of them. And for example, in 1 + 1, the boundary divergence, it will be just localized at the endpoints of R. And so the volume dependence is not affected by this. So what I'm going to show just in a few slides that this charge fluctuation entropy has unbounded growth of volumes in three theories and in gauge theories of weak coupling. And just in a few more slides, I will show that it actually leads to a black hole information paradox. So there are many black hole information paradoxes. So why should we care about this one? So first of all, it's as I said, it's a replica-free calculation, so we cannot be saved by replica wormholes. Also, what I need to compute in order to get a paradox is not a complicated thing. This is just the expectation value of the simple observable, which just measures the charge of the Hawking radiation. I don't need to collect all the radiation and put it in a quantum computer or anything like this. All I need to do is just measure the charge. And for global symmetry, you can say that the resolution is that there is no global symmetry. But then the question is what happens with the gauge symmetries. And so my talk will be mostly about that. And with Amir, we came up with a few resolutions, but the one I would like to highlight, although I will also mention the other ones, is that at least in 1 + 1 GT gravity, the gauge coupling has to be big enough. And this is compared to the gravitational coupling. And then it's similar in spirit to weak gravity conjecture in 4 dimensions. Okay, the plan is, as I said, first I will demonstrate that this quantity grows with volume, and then it leads to a black hole information paradox. Then I will describe the resolution in the gauge theory, and then I will mention how this computation generalizes if I assume that I have an ensemble instead of a single theory. And finally, I will end my talk with a certain puzzle which we haven't been able to resolve. Maybe some of you will be able to resolve it right away. For free massless Dirac fermion, the computation is really elementary. You can bosonize the U1 current, and then this computation of this matrix element literally becomes a computation in a free massless scalar theory in 1 + 1. So I trust everyone in the audience can do this computation. I will just state the result is that the charge distribution is Gaussian. And in the limit, when the interval length is much greater than beta, the fluctuation entropy is given by this logarithmic growth. So x is the length of the interval, the volume essentially. And if I want to make it to scale with the central charge, I can say that I have a large number of abelian groups, and then it will be literally multiplied by a factor of c. If you don't like large abelian factors, you can also study this quantity for non-abelian groups, but then this computation is not so elementary. So this is obviously a problem. If I go to East Coast model and the eternal black hole, then I can study the region R, which is shown in red. And at some point, just the entropy of the charge fluctuation in region R, it exceeds the black hole generalized entropy. And this happens at this time t star, and this is obviously a problem. So S0 is the extremal entropy of the black hole, beta is temperature, and phi r is the renormalized dilaton value in JT, which is the gravitational coupling in JT essentially. Yes?
If we put back in the cutoff, like the one that we use to regulate the entropy, how would it appear in T star?
I think it's this subleading. I essentially hidden it into this factor here. So it doesn't depend on the central charge. It's just some extra logarithmic behavior, which is, further one compared to S0 or C. So it's not really important. So this is the effect of, so this time is of order e to the s naught divided by c. But if both of them are large, this is fine. And actually, exactly the same time scale, even with this factor of 4, recently appeared in the paper by Ahmed and Henry, but in a different context. They studied the entropy of the coupling distribution. So we argued that because this is effect of order s naught divided by c, the non-perturbative effects of order e to the minus s naught are not important. So assuming that we have a global symmetry, we have a paradox, but presumably gauge symmetries should be allowed. So let's move on to gauge symmetries.
Could you clarify one thing about the setup? So the previous transparency. So if I understand correctly, you have to go to very late times, right?
Yes, that's right.
Why don't we need to include an island?
Because I consider only one copy of the system. So how would you include the island? I just compute a matrix element of an operator.
Okay, now I understand. Sorry, yeah, thank you.
Yeah, this is kind of the salt of this story.
Yeah.
So gauge symmetries. So first of all, we need to talk about what's the entanglement entropy if I have a gauge theorem. In this case, this decomposition from my second slide, it gets a promotion and becomes a definition. Because if I have a region R in the gauge theory, the hyperspace doesn't factorize. It does factorize if the charge inside this region is fixed. So, and coupling to Young-Mills theory in 1+1 is easier because massless vectors, they don't have propagating degrees of freedom. So it definitely wouldn't contribute to the volume dependence. I have no replica copies, so the topology of my manifold is trivial, so I don't need to include extra holonomy degrees of freedom and so on. And the most importantly, the gauge coupling has a dimension of mass. So it means that at small distances, I have a weak coupling. So for if T star is less than the inverse coupling, then I can just trust the above computation and take it as it is. And then the problem persists. However, if the time is actually greater than the inverse coupling, then the charge is actually confined. So it's a well-known effect which happens in both abelian and non-abelian cases. So in the Bose-Nice language, this operator phi, it acquires a mass. So the charge is confined and the fluctuation entropy stops growing. So the proposal one can make is that this two-dimensional gauge coupling, which does not run, by the way, should be bigger than the all possible values of inverse T star. And one surprising thing that actually this function, it does have a maximum. It leads to the following. So C is the one I wrote here, it's for abelian case. So C is C Dirac fermions having U1 to the C symmetry. And S naught again is extremal entropy. So there are obviously a few cross checks we did. So one can imagine setup where the symmetry is gauged in the gravitational region only. Whereas in the flat spacetime region, it's a global symmetry. So one has to do some things. One has to be careful of the boundary conditions and so on, but this computation is doable. And in this case, exactly this value of the gauge coupling, it suffices to escape the problem. Also, we looked at possible hints in SYK for such a bound. And if it's true, one can couple different SYK dots. And then it's indeed the case that the two-dimensional gauge coupling is greater than the C divided by phi r. So in SYK language, phi r is the heat capacity, and the gauge coupling is inverse charge suspensibility. And finally, maybe the most surprising thing is that there is a top-down approach to GT gravity, where you study the theory near the horizon of some extreme black hole. And if the black hole is magnetically charged, in this case, you can have fermionic matter propagating along the road. And in this case, one can map all these two-dimensional parameters to four-dimensional ones. And surprisingly, since the four-dimensional coupling enters in both sides, what we get is that the four-dimensional theory should be weakly coupled at the horizon scale. And this is very natural assumptions which you have to do anyway if you really want to have this setup under control when you reduce four-dimensional theory to two-dimensional one. Surprising. So let me now comment something on ensembles. So if I have a normal quantum field theory, then P of Q is a P of Q is a P of Q. I can compute it by whatever means I have and just plug it inside the definition of the Shannon entropy. But if we say an ensemble, if we have an ensemble, then really what we have is the conditional distribution of charge given the ensemble member. And then what we computed in our paper, essentially we computed this in a semi-classical gravity. So it really yielded some coarse-grained charge distribution. But this quantity is still a good quantity if you trying to compute the charge correlation functions in the gravity, because the charge does not, definition of a charge does not depend on the ensemble parameter. But then it's perfectly fine that this coarse-grained charge distribution has large entropy. What we really should do is to compute this Shannon entropy for each ensemble member, and only at the very end average over the ensemble. Because of the concavity of the entropy, this quantity is always smaller. So one brief comment I would like to make, but presumably it's many people know it in different forms, is that one can come up with this equality, namely relate these three things: the entropy of the ensemble, the entropy of the coarse-grained distribution, then the average fine-grained entropy. And this inequality also has like a fourth player, which is some weird thing, the ensemble entropy given the fixed charge. So I don't really know what it is, but what I know is that it's positive. And then the unbounded constraint, fluctuation entropy implies that the ensemble entropy is unbounded. Although there are certain caveats for defining the entropy for continuous distribution. So if you want to take it as it is, you should assume here that J is discrete. Otherwise, in some sense, entropy can be negative for continuous distributions. So, okay, I actually have time. Okay, let me now comment on islands. So what's the deal with the islands? Is that if we want to compute the phenomenon, the fine-grained phenomenon entropy of radiation region R, we follow this stream of surface prescription, which involves just the CFT semi-classical phenomenon entropy of region R union island. However, if I just take CFT and consider the reduced density matrix for two intervals, the charge which is defined for my original region R does not commute with the semi-classical density matrix, the total charge QR plus QI commutes, but the individual ones do not. And for global symmetry, it leads to charge non-conservation, as was emphasized in the paper by Mink and Henry. So for in the gauged case, there should be a way around it, and indeed, in their paper, Mink and Henry pointed out that obviously we have gauge symmetry, and again, there should be like two universes in the form of the planes here and on the upper side. I now have an extra closed cycle in my geometry, so I have to integrate over the boundary conditions as the matter fields go through the island. And this can be represented as the insertion of this operator. So yeah, if I integrate over the phase gamma, then the charged particles propagating along the throw, they give a zero contribution. But we try to push it a little bit further and see what kind of expression it really leads to if you try to compute the entropy, whether it's big or large. And we run into a certain conceptual problem, because naively, when you look at this picture, at this integral, so you can think about this island as a branch cut in the usual CFT language. And then it has an upper part and lower part. And this integral, it goes on the upper part and the lower part in the different directions. So really what it does to a density matrix, it addresses it by these two operators, on the left and on the right. And in fact, this expression, it's natural, and it has very nice properties. This density matrix on the left, it's positive definite. It has unit trace. But unfortunately, in general, this transformation, it maps pure states to mixed states. So in this prescription, if you try to, so the original island prescription, for example, it respects the purity of the state. If you try to compute the entanglement entropy of the whole system in the East Coast model, you get zero. If you try to compute it with this prescription, you get something positive. So this is some conceptual problem we haven't been able to resolve. So let me just summarize. So fluctuation entropy is a simple quantity which can be used to bound the entanglement entropy from below. It's easy to compute, there are no replicas, and this charge operator is simple. So it does not do any complicated stuff with the Hawking radiation. Gauge systems or weakly coupled systems, it grows with the system size logarithmically, and in certain scenarios it poses a black hole information paradox. If the charge is confined, then fluctuation entropy stops growing, and we used it in 1+1 JT gravity to bound the gauge coupling from below. So let me list some open questions. So first of all, it's the question about the proper island prescription when I have a gauge symmetry. Maybe the most important open question is that what happens in higher dimensions, because the fact that all gauge symmetries are confining, it's a feature of 2 dimensions. In higher dimensions, we know that QED is not confining. And I don't have a good answer to this question, except that for non-rotating black holes, the radiation is dominated by low angular momentum modes. So maybe as far as the computation of charge correlations are concerned, I can always use some 2-dimensional prescription. And the last very speculative comments, I need 10 seconds. Okay. So one speculative comment, but it's related to one physical feature which is very, which I really like. is that we argued, and we have some technical arguments in the paper, that effects of order e to the minus s naught, which can come from baby universes, are not important. But one can imagine that we have effects of order e to the minus s naught divided by c. So I'm not aware of any proposals why such contributions would arise, but they would affect the conclusion. And it's very reminiscent of IR renormalons in the Young-Mills theory. So in the Young-Mills theory, you have instantons with integer topological charge, but for certain physical effects, you need to argue that this instanton with integer topological charge can split into n constituents with fractional topological charge. And in this case, it would be similar to a fractional big universe where the Euler characteristics is 1 over c. So I should mention again that I don't know any other places in the literature which would require aiding such effect, but it's just some analogy. Okay, thank you very much.
Yeah, can you just clarify, I didn't quite follow some details. So does the problem only happen if you have charged particles that are massless, or is there a problem if they're massive charged particles?
Okay, good. Yeah, I completely evaded this issue. So in this setup, what we looked at is it was massless matter coupled to Young-Mills, and then I argued that the Young-Mills coupling has to be big enough. I believe if the mass is positive, then the allowed value of the gauge coupling can be smaller. So I believe for very massive matter, you wouldn't run into such a problem.
Yeah, naively, that's what it seems like, is that you wouldn't have this problem if the charges are massive. Because I'm trying to understand how to extend to higher dimensions. So I guess QED in 3+1 dimensions with massless charged particles is a bit confusing.
Yeah, that's true.
All right, well, thanks.
But again, you will have to compare. Essentially, I think the fluctuation entropy will stop grow of timescales of order 1 over mass. So depending on your situation, it might be big or long timescale. In this case, you will need to impose some lower bound on the mass. Your massive particles can be too light.
Thanks.
May I ask a simple question? So, could you explain again why you don't have a replica and you don't have an island? Is these two are related?
Yes, right. So it's because I simply compute the expectation value of this operator. So when you compute matrix, you pick up your favorite density matrix and you compute its matrix elements. You typically don't need to introduce replicas. So it's just one matrix element.
So that's why you don't have island.
Yeah.
Does this mean that you don't really couple to gravity?
The theory is coupled to gravity, so this CFT it's free to propagate between the flat space-time region and the gravity region. So it is coupled to gravity.
So in some of your bounds, you had a factor of e to the minus s naught over c, right? But in your four-dimensional, the bound on your four-dimensional coupling, there wasn't such a factor.
Yes, right. I think.
It disappeared.
Yeah, I think this factor it becomes literally this factor s naught over c. It literally becomes 1 over four-dimensional coupling for the setup we considered. Because we looked at in this setup, you want to take magnetically charged black holes with their charge 1. So you can imagine that you have U1 to the C gauge theory in 4 dimensions, and then you have C fermions. And then in the 2 dimensions, you don't want the amount of matter exceed the amount of the gauge symmetry. So this is why the magnetic charge here is fixed to 1. And because of this, it's becomes 1 over 4-dimensional capacity.
So the entropy of that black hole is of order the number of particles that is propagating.
Number of particles times 1 over g.
Okay, very good.
The map, you have this map with the insertion of actual holonomy. Does that map preserve trace?
The map, yes, it does preserve trace. So when you take the trace of both sides, on the right side, you can, annihilate the Q operators. And so you are left just with the.
Actually, what is gamma for the?
Gamma is a number. It's and the integration goes from -pi to pi. So you're easily dressed by these, these notations.
Could you just explain the claim that this rule maps pure states to mixed states? So I maybe missed it.
Yeah, I'm sure you're familiar with this. So this is completely positive trace preserving map. So you can think that you can say that the integral is a
Oh, sorry. You just mean, yeah.
It's a discrete sum, and then or you just have a sum.
I guess I'm confused as to what the problematic issue is. Where the problem?
Yeah, the problem is so the island prescript. Suppose I'm in the slide. So suppose I want to compute the Fluctuation Entropy in this setup of the whole spacetime region, including this like a dot. Then the usual island, it will just stretch between the endpoints of the region R. And so this R union I, it just becomes, the whole interval. So the entropy is 0.
But now we have a different topology for the, like
Sorry,
the whole thing is connected, right? It's not an island anymore. It's just so I would have said that you don't need to do the
no, I'm trying
boundary to the island. If you're computing, you're including the quantum dots, you're including the holographic.
Yeah.
You're computing the whole thing. Then I would have said it's not an island. It's the topology is it connects to the conformal boundary. So I wouldn't have used the same rule. The same way we don't include the area contribution of the conformal boundary. Right, that would be formally infinite, but we don't include it because that's.
But he's not including the area.
Yeah, but he is including the. He is projecting the gauge subselection segments. I don't think you need to do that either, unless it's like an actual boundary, not a conformal boundary.
You don't mean to suggest that there's a replica wormhole in this calculation?
Yeah, there's no wormhole. It's just
well, I still believe that in this case you might run into some problems with the purity. So
forget about your island rule. Just do the replica-free calculation. Right? What's the topology? It's just a disk, right? Or let's see, 2 disks, in fact. It's just twice your original thing. Like, of course, you're going to get 0. It manifestly cancels.
Yeah, but I think okay, yeah, there might be some issue with this charge conservation if your space-time regions have a funny topology. So now, if you include the whole system, I think you might still want to integrate over these holonomies, just because you would still wouldn't want the charge to hop between the replica copies. But okay, maybe we can discuss it like after the talk.
Yeah, just very brief comment. Like if you're swapping the entire system, then trace row squared is exactly the same boundary conditions, exactly the same conditions for your path integral as in the normalization where you have trace of row whole thing squared. So whatever rules you're using for one, you should be using for the other. So you should manifestly give one, which corresponds to an improved theory.
No, but you could have a mixed state on the Cauchy slice.
You could, but you don't.
Well, that's one way that you get non-zero.
Well, but there, your gravitational path integral, you'd have to be summing over correlated bras and kets, and you're just not doing that. The way the path integral, you know.
Yeah, I believe in this case, since you're still extending this branch cut, you would want to disallow your charged particles to cross this I, and this is why you will still have this integral, which will produce non-zero entropy in this case.
We can talk about offline.
I think if you include everything, the charge operator you had should include the integral of the current in the red region plus the value of the electric field at the boundary. That's the total charge.
Yes, you are saying that now I have to include the charge of this YK dot as well.
Yeah, that's right.
Yeah, maybe.
And that you can express as the charge of the blue region and so on. And then you can...
Okay, yeah, maybe in this case it's indeed possible to avoid it, but in general it just seems fishy that what I call the semi-classical density matrix in the gauge theory, it can be mixed, although you started from a pure state. So maybe in this case it wouldn't lead to a problem, but I still would be cautious.
Final questions? No, that's thanks. Thanks again.